much. Good morning, everyone. Good afternoon, everyone. My name is Gianluca Demartini. I am currently faculty member at the University of Sheffield in the United Kingdom. Next slide, please. Just one slide background about myself. I'm fine. Okay, then. All right. So my background is in computer science. I got my bachelor, master in computer science in Italy, my PhD in computer science in Germany, and then I worked in Switzerland, Spain, US, and currently in United Kingdom, where I am a faculty member in the social sciences. I'll tell you more about my research in the second part of the talk. So the plan is I will spend about 20 minutes give you a general introduction on big data with potential challenges and opportunities, and then I will, in the second part, focus more on my own research work, just to give you some insights of the topics I'm working on. So before going into the content, let me just tell you about ACM. ACM is a professional body that aims at supporting computer scientists or people working in computing, and it touches academics, industry people, as well as students. So it really aims to bring together all these people working in computing topics. But of course you know all about ACM already, since you are the winner of the programming competition they organize. So my talk is also gently sponsored by ACM through the Distinguished Speakers Program. All right, so let's talk about big data. And of course, let's start with a definition of big data. The classic way to talk about big data is by means of the V's. Originally there were 3 V's, and then people started to add more and more. So the 3 main dimensions of big data are volume, variety, and velocity. So the obvious one is volume, right? It's just about the size of the data you can deal with today. So we can now talk really about petabytes of data of content that we may want to use or analyze or to extract knowledge out of it. But it's not just about the amount of data that we need to deal with. It's also about variety. So this data comes in different formats. We have to deal with text, with images, more structured content like databases, knowledge graphs that connect entities and objects one each other, up to plain text like blogs or news articles on the web. So it comes in very different formats, and it starts to get challenging to bring all this data together because of the variety of formats it comes with. And the third dimension is the velocity, so the speed in which data comes from. On one end, you can just assume all your data is there, stored on some hard drives, and then you can take your time to analyze it and extract the knowledge you want from it. But in some cases, data arrives over time. So think of time series, think of Twitter, where you have tens of thousands of tweets per second that arrives against your system. So you need to design systems able to deal with this velocity dimension, so dealing with data streams, rather than just having the data stored on the platform. Thanks. So volume. There is a lot of data. Just to give you a couple of numbers, think of Facebook, an online social network platform. It's processing probably today more than 1,000 terabytes per day of data, and it keeps adding tens of petabytes of storage every month to store images, videos that people upload and stream on the platform. So this obviously requires a lot of computers, as we will see, just to store all this large volume of data. The point I want to make is that it's not just the internet, big internet companies that have a data volume problem. The same, probably at a different scale, but still having too much data to deal with is a problem that banks, city council, governments, shopping markets, and so on still have. Think of credit card transactions that banks store, or fidelity card that supermarkets give to customers, and every time they buy something they will scan it, and this will generate very large amounts of data. Next slide. So the other dimension is velocity. So Twitter has been growing a lot over time in the terms of data they deal with, and the average tweets per second is in the order of a few tens of thousands, so you need to build systems able to deal with this. But what's even more challenging is that there are peaks in the distribution of tweets per second. So you have events like earthquakes, or Justin Bieber published a new song, and in these situations you have peaks of hundreds of thousands of tweets per second. So the systems you need to build must be able to deal with the peak loads of data streams that can be observed. So we'll not go into the analysis of this data. I will really want to talk about the systems that are necessary to deal with this amount, velocity, and variety of data. Again, like before for the volume, it's not just big internet companies that have a data velocity problem. So think of stock exchange market where you have many transactions per second. Think of sensors, smart cities where you have water pipe networks in the city, and they have sensors all across the network that keep generating data all the time, and you need to identify failures in real time in order to send an engineer in place to fix the fiber optic cable. So we work with Virgin Media in the UK, and they deploy fiber network cables around the cities, and they have all this data coming to one single data center, and they need to decide how to deploy engineers to check and fix fiber cables. And so on, fitness trackers, wearable devices, all these generate data as a stream, and if you think of one unique central point where this data arrives, then you have a data velocity problem. Next. Okay, so these are the problems. How can we deal with this type of data? Well, you have two options, right? You need more powerful computers than what we used to have or what we have at home. And you have two options to get a more powerful computer. One is to scale up, and the other is to scale out. So historically, what we used to do is to scale up. We build a more powerful computer, a mainframe, where you have a lot of disk, a lot of memory, very strong processors, and you have this amazingly powerful server that can do more than the computer you had 3 years before. So this is scaling up. You build a more powerful machine. But this reaches a limit, right? There is only that much you can do. And with the amount of data growing and growing, you have limits on how much you can scale up. The alternative, which is what is now more popular, is to scale out. So rather than having one super powerful computer, you actually use many standard computers, and you distribute data and computations over them. So this is how you scale out. This is a data center that Facebook built. This is a building. That's a truck, just to give you an idea of the size of the building. And it's built in Sweden because they use the outside cool air to cool down the computers they have inside. So inside this building, if you can go to the next slide, it all looks like this. It's long corridors full of computers. Each row computer, and then you have many computers in each column, and then you have this long corridor of many computers. And the entire data center building is looking like this. So each of the computers in this picture is nothing really amazingly powerful. It's more or less the same as you could have at home or your laptop. It's nothing more than that. But what they do is they scale out, right? So they have very many of these computers, so they can distribute data and computation over data on this type of architectures. So basically, all the pictures, videos, and posts you may upload to a website like Facebook, they will be stored here and replicated across the data centers all over the world. All right, so to scale out, to deal with big data, we need a lot of computers, as we understand. We need to fill these data centers with many standard computers. So just to give you some numbers which are outdated by now, so think of this number as being much bigger today. Google is using more or less 1 million servers, and this consumes a lot of electricity as well. So as we saw, Facebook is using outside air to cool down the computers because they heat up a lot, but they also consume a lot of electricity. A number that really amazes me is that Google computers roughly account for 0.01 of the global world energy consumption, which is, I mean, 0.01 is not a big number, but thinking that just computers use that much of all the electricity we use in the world, it's quite a lot. In comparison, the CERN Large Hadron Collider that is accelerating particles in Geneva is consuming less than Google computers. Of course, Google is carbon footprint at 0, they pay back, they plant trees and all this stuff to decrease their impact on the environment. Next. Okay, so we have these very many computers. How can we deal with our volume and velocity problems by using many computers, by scaling out? I will not go into the details, but just to give you the main pieces of technology used in this type of infrastructure. You have these fundamental papers being published all by Google engineers. They started with the Google file system, which is basically a distributed file system over these large clusters, over these very many computers. So what happens is that each of these computers may have 1 to 4, 8 different hard drives, and then you have thousands of these computers. What the GFS, the Google file system, allows you to do is to see one single file system on top of these very many machines and hard drives. So you have a file system of petabytes capacity, which is then managed by the file system across many different hard drives, replicated many times because these hard drives will fail regularly. They are just standard hardware that you can buy in a shop, so they will fail. And to preserve data, data will be replicated around. On top of this, they published around 10 years ago Bigtable, which is a structured data storage system. So they use key value per data structures to represent data across this cluster in the data center. And then on top of that, you have the computational paradigm, so MapReduce, that allows you to make computations over this data. And again, how this paradigm works is by distributing and parallelizing computation across the very many computers you have. So rather than processing from the beginning to the end petabytes of data, you split your data across different computers, and in parallel, you process them so that you can finish faster than just by linearly scanning all the data you may have. All right, so these were really academic papers. These are systems that Google built internally, probably years before they published, and then at some point they decided to publish these to the academic community. And what happened is that after they published these papers, the community started to work on all these systems. So they implemented these systems, they released them open source, and what we have today is the open source analogous of the Google file system, which is the HDFS Hadoop file system, and so on. And the analogous of MapReduce, which is Hadoop. So these were re-implementation of the Google solutions that they published, and then this became open source. It was contributed by many different people across different companies, and it's something which is now available to everyone. Again, on top of this, then we have an ecosystem of different open source solutions. It's not just these three ones, but we have much more. Today, probably the most popular solution is Spark, which is an integrated solution for many different big data problems. Okay, so this is what big data is, why it is difficult to deal with, but also which solutions and which systems we have to deal with this. All right. So as I said, I have a computer science background, so I can tell you all about systems and how to deal with any big data problem you may have. But let's also think about the implications of having this data available and who owns the data and who is collecting the data and what they are doing with it. So this data is there, and the question is, should we care or should we just enjoy the services that we are given for free? The ability to share with our friends, the ability to access our data anywhere because it's stored in some data center in the cloud, and so on. So let's think of which data it's being collected about us. If we use online email clients like Gmail, online social networks, if you have a debit card we pay at the shop with, if you have fidelity cards we collect points with, if we have a metro card then we enter, tap in and tap out at the metro station, if you have a mobile phone that is counting our steps, and so on. All this data is being collected and it's data about us. So as long as we get reminders that we should work more, if you get a notification that a friend of us shared a picture, that's all good. It starts to be less nice when we apply for a mortgage and then they decide, based on the data they are able to access, whether we should get or not get the mortgage. Or again, whether we should get an health insurance and how much we should pay based on the number of steps we do every day. So we are getting more and more in a situation where algorithms decide what we get and what we can do, and I will give you examples of that. On the other hand, on the positive side, not all of this data is accessible to others to read. So one example I can give you is that if you use Gmail as an email client, the emails you store and you write and you receive there cannot be read by any human being, even if they are Google employees. They have no access to your personal emails because all this is encrypted, and despite agencies claiming they can decrypt content, this should be safe and no human being should be able to read your emails unless they have your passwords and access credentials and so on. But what happens is that algorithms do read your emails, and you are presented with advertisements, suggestions based on your email inbox, and that's in a way accepted from an ethical point of view. So you have a piece of software going through your inbox and deciding what type of advertisement and content you should be presented with. So let me give you another example on how algorithms decide what we see, as in the Gmail example, but also what we do. So Uber, as you may know, is a mobile app that allows you to book a car that will drive you from A to B in exchange of some money. You have drivers and you have people who are driven from A to B. And the person driven is paying money to the driver, And who decides how much money is a piece of software, is the app itself. The more demand for cars, the higher the price you will pay for the ride. So the prices of these Uber drives are decided by a piece of software, but then let's think of these drivers. These drivers are doing this as a job to get a salary at the end of the month, and how much money they make is decided by the piece of software. Even worse, whether they are getting a ride or not is decided by the app. There is no human person being the manager saying, now you go there and you drive this person, and now you go there. It's all done by a piece of software. So now we are moving in an age where algorithms and software decide how we work, how much money we make, how much we work. Of course, we can always decide not to use these things, but in the end it's becoming a standard de facto that we cannot really avoid. Okay, so I depicted this very dark scenario where data, computers, algorithms, and software rule our world, and it's all bad. So let me give you some positive examples as well. Again, something which was possible thanks to data is understanding how we learn foreign language. The example here is Duolingo, which is an app and a website where you can learn a foreign language. Many thousands of people use this website to learn a foreign language, and thanks to the data they collected of people learning a foreign language, they understood that based on the different native language you come to the website, you will be better off in learning the language if you start with certain skills or other skills. So for example, if you are an English native speaker, you learn Spanish better starting with some vocabulary, but if you are a German native speaker, you start better off with some grammar rules. And just by trying A/B testing over different people, they could reliably observe this phenomenon, which was not really known before. So again, this is an example where data allows us to understand how we learn better. Or language translation. So language translation apps are also driven by data. There is machine learning in the background, but all this needs data to really work and be trained. So it's people feeding examples to these algorithms to make them work. Okay, so all this brings us to data science, which is the new hot topic at the moment. Harvard Business Review labeled this as the sexiest job in the 21st century. So the problem here is that we have all this data available. So as I said, it's not only internet companies, it's basically any company is collecting data just because they can, but they don't really know how to extract information and knowledge out of this data. What they want is data-driven decisions. All the companies I talk to, they have data, they have super interesting data, they store it because they can, and they want to base their decisions, their strategical choices, based on the data they have, but they don't really know how to do it. So what we do need is data scientists. In Sheffield, we have a program in data science where we try to teach students from any different background data science skills. So we do have people coming from health, psychology, sociology, and we teach them data science skills so they can go then back to their original domains and apply the skills they have to help making these data-driven decisions. Just as a few examples, our students went to work for cancer research, the housing market companies, telecommunication companies, and so on. All right. So this was the end of the first part. It was really just a very quick overview of what big data is, the systems we can use to deal with big data and the implications of having this data available